Okay, so we will start with our lecture for today. Yeah, so the lecture for today is going to be about arenes. Yeah, arenes. Okay, the one inside our syllabus, we are going to learn about benzene and methyl benzene. Yeah, so let's actually look at what are the things that is important that we need to cover over here. So at the end of the lesson, you can. This is taken from your syllabus. Yeah, there are some changes. Okay, there are some new parts being added because of the change of the syllabus. Yeah, so we will actually go through all the 4 points over here today. Yeah, so the first thing that we need to know is about benzene. Yeah, generally all of you should know. Yeah, benzene is going to be having the formula C6H6. Yeah, so the shape of benzene, yeah, is going to be is hexagonal shape, and it is made of 6 carbon atoms. Yeah, so all the organic hydrocarbons, yeah, with the benzene ring. Hold on, let me mute all. Sorry, guys. Okay. Hold on, yeah. Let me check. Okay, so let's continue. Okay, so if you look at organic hydrocarbons, yeah, with benzene ring, okay, they are going to be called as arenes. Yeah, arenes, or they can be called as aryl compound or aromatic compounds. Yeah, that's why when we look at the lecture, yeah, this one is going to be known as arenes. Yeah, so arenes are going to be organic hydrocarbon that has benzene ring. So the simpler structure is C6H6, and the structure, okay, in the beginning, yeah, it's actually this is the structure. It was proposed by Frederick August Caie. Yeah, so Frederick August Caie, he proposed this particular structure, and it was known that benzene is going to be planar, perfectly symmetrical, and so on. So Frederick August proposed this structure, and as you can see, this structure, because we want it to satisfy C6H6, okay, therefore, okay, August Caie suggested that in order to get C6H6, you need to put the 3 double bonds over there. Okay, but later on, yeah, you can see the 3 double bonds over there. Later on, okay, they actually found out that, okay, there are certain evidences, okay, that say that you cannot accept, okay, the previous benzene structure that has the double bond, the 3 double bonds over here. So one of the evidence, okay, the first evidence is going to be, later on we have found, you can see from the table, okay, they have found the bond length, okay, of carbon, single bond carbon, okay, is actually longer, okay, compared to carbon, double bond carbon. So therefore, okay, if you want to actually say, if I want to draw, because the carbon and carbon is longer, so if I draw carbon, carbon longer, carbon, okay, to another carbon double bond is shorter, okay, this is supposed to be shorter, longer, okay, this is going to be longer as well, and then shorter. If I draw this, okay, it's supposed to give you this structure, yeah. So if I put the double bond over here, okay, and you can see earlier it was suggested that it must be a perfectly symmetrical molecule or hexagonal structure, okay, but now, okay, what you have over here is going to be a structure which is going to be a distorted shape, yeah, a distorted shape. And later on they found out that, yeah, the carbon-carbon bond in benzene is not actually similar to carbon single bond, and it is not similar to carbon double bond. It's somewhere in between, okay, or to be exact, it's closer to carbon double bond, but it's going to be 0.139, as you can see from the table. Okay, so it is not right, yeah, to represent the benzene structure using 3 double bonds over there. Okay, so that is going to be the first evidence, okay, that actually Caie have to change from this structure and suggest this particular structure, which has a circle in the benzene molecule. And you can read more about this. Okay, actually, Caie have a dream, and he actually found out that he had a dream of a snake biting its own tail. Yeah, so basically he said that, yeah, instead of drawing 3 double bonds over there, let's actually put it as, okay, a circle, okay, showing the electrons are going to move around, yeah, in the benzene ring. So he came up with this model. Yeah, so this one you can read further. Okay, but there is going to be another evidence apart from the bond length, okay, that can actually reject the old benzene structure. Okay, the another evidence is going to be, okay, because we have learned that, okay, alkene, they will undergo electrophilic addition reaction, yeah, because of the carbon-carbon double bond. And in this structure, the old structure, yeah, Caie proposed that there were 3 double bonds over there. If you have 3 double bonds, supposed to be, it will undergo electrophilic addition easily, way easily compared to other carbon-carbon double bond, yeah, because it has 3 double bonds, yeah. But they have found out that benzene, they require harsher condition, yeah. It means it requires maybe higher temperature, higher pressure to go through addition reaction. And they found out that benzene, they prefer not to go through addition reaction. They prefer to go another type of reaction that we will discuss later. This is going to be because of the benzene ring itself, because the benzene ring will stabilize the benzene structure. That is actually, the stabilization is called as aromatic stabilization. Yeah, this one later we will also discuss about this. But, okay, everyone should know, yeah, whenever you have a benzene molecule over here, if you have bond with hydrogen, bonded to carbon, bonded to another carbon over here, each carbon atom, it has 3 bonds over there. And you should actually go and refer to hybridization. If you do not understand about the concept of hybridization, go and actually read about hybridization. There is a video in my channel also about hybridization, okay, where if you have 3 bonds over there, 3 sigma bond over here, you need to have hybridization. You need to have 3 orbital. In order to have 3 orbital, you must have 1 s orbital and you must have 2 p orbitals. Therefore, the carbon must be sp2 hybridized. Yeah, if you do not understand, yeah, there is going to be another lecture or another video also on this. Okay, please go and check. Yeah, you can check with your teachers as well. So therefore, okay, each carbon in the hexagonal ring is going to be sp2 hybridized. And each carbon atoms, yeah, they form how many sigma bond? You can see all these are sigma bonds. So 1, 2, 3. Each of them, they form 3 sigma bonds, yeah. And each of the carbon atoms, okay, they contribute, yeah. They have 1 more electron. Each of the carbon, they have 1 more electron. Okay, they will be contributing the electron to the pi bonding. It means, okay, there is going to be another 1 more electron, okay, for each of them. They will contribute, okay. It means the orbital for that is not hybridized. They will contribute to the center, and this electron, they start to move in circle. They can move around, okay. They can move around, okay. This is what we call as delocalization, okay, of the pi bond. Yeah, so in this case, they say each carbon atom contribute 1 electron, and they will become delocalized over 6 carbon atoms in the hexagonal ring. Okay, not only at the top, and also at the bottom. Yeah, please remember that. Okay, so they move around. Okay, the difference with this, with the normal or typical carbon-carbon double bond, okay, is going to be if you have pi bond. Yeah, if you have pi bond, okay, they actually able to move also. Yeah, but they are able to move within, okay, within, let's say, from here to here. Yeah, so they are going to be able to move from this carbon to this carbon, this carbon to this carbon. So if you have another carbon over here, okay, another carbon over here, the electrons are not able to be delocalized up to here. Yeah, so that is going to be the difference when it comes to benzene. Okay, benzene, the electrons, they are not attached to a particular carbon. They can move, yeah, from this carbon, they can move to this carbon also. So they move around. Okay, that is going to be the difference when it comes to benzene. And this movement of electrons is very, very important because I mentioned to you just now, aromatic stabilization. Okay, the stabilization is there. Yeah, so you can actually go through that. Yeah, the next part that we supposed to learn under benzene is going to be basically naming the aryl compound. Yeah, so the naming part, yeah, can be sometimes confusing because last time we learned about the side chain. Yeah, like for example, if you have CH4, okay, CH4 is known as methane, but if I have CH3, the side chain, I call it as methyl. Okay, the same thing. Okay, if you have benzene, okay, if you have benzene, each of the carbon, they have hydrogen, okay, bonded to it. So if you go and add something or you substitute one of the hydrogen with something, okay, let's say, for example, I substitute with CH3, okay, what happens, okay, from C6H6, okay, because you substitute the hydrogen, they are going to become C6H5. Then you put the CH3, the newly added part, yeah? So this one, they will function like something like methyl, and they have the name also, okay? The name is going to be known as phenol, okay? But this phenol, yeah, this phenol is not used most of the time in naming, yeah? It is only used, I think, when it comes to phenol, yeah, and when it comes to amine, yeah? But under normal condition, you can see from this table over here, if I have, okay, if I have, like, for example, you see here, Cl is replacing the hydrogen. So this one's supposed to be C6H5Cl. I don't call this as phenyl chloro or something. Yeah, I call this as typical like chlorobenzene. Yeah, like normal. If you have Br, then I call it as bromobenzene. No problem. Yeah, like similar. Yeah, if you have this NO2, NO2 is known as nitro. Yeah. So if I have this, okay, I supposed to have C6H5 because one of the hydrogen is replaced by NO2. So this is going to be NO2. And I call this nitrobenzene. I don't call this as phenyl nitro or something like that. No, yeah, it's nitrobenzene. Okay, but when it comes to phenol, things are going to be different. Yeah, the phenol is going to be C6H5. Yeah, and you replace the H with OH. So I have this because alcohol, we tend to call it as what? Ethanol, propanol, okay, butanol. Okay, so I don't call it as benzol. Yeah, so it doesn't make sense. So they actually changed this. Okay, this is the part that I told you, phenol, and you have all. Okay, so they combine this and the name is going to be known as phenol. Yeah, that is why you have phenol. Yeah, and then you have this sometimes. Okay, we need to follow the common one. You can see this one. This is a phenol, like just now we learned. Okay, if you say this is phenol, automatically this is going to be carbon number 1. Okay, because you are referring to phenol. Okay, and if you're referring to phenol, automatically this is going to be carbon number 2, carbon number 3, 4, 5, and 6. And the Br over here, there are 3 Br, so we call it as bromo. And it is going to be 2, okay, and then 4, and then 6, okay, tribromo, okay, tribromo, and then you put phenol. Okay, no need to put 1 all or something like that. Okay, straight away use phenol. And another one, okay, over here is going to be, again, I told you C6H5 because one of the hydrogen is replaced by NH2. So NH2 is amine. So now, okay, I don't call it as benzene amine or amine benzene. Okay, I am going to call this as phenyl amine. Yeah, so you need to remember the term phenol, yeah, phenol is going to be used when it comes to phenol and phenylamine. Okay, for certain cases, we use benzene. Yeah, this one is just a heads up for you. Okay, but if you look at the checkpoint now, okay, if let's say we put over here, how many electrons, okay, are involved in the pi bonding in a benzene molecule. Yeah, the pi bonding is going to be the electrons in the circle over there. And I told you, each one carbon, they will donate one electron to the ring. So therefore, okay, you have 6 carbon, automatically the answer is going to be 6. And for second part, which type of atomic orbital do this electron come from? Okay, this one is going to be because of the carbon. Yeah, carbon is 6. So 1s2, 2p, 1s2, 2s2. I'll write the electronic configuration. And then I have 2p2. Okay, and if I put this is going to be the ground state. Okay, this is more towards your hybridization. Yeah, and then it will become the excited state. Okay, what is going to be the excited state? If you have 2 electrons here, okay, 2p2, so you have 2 electrons over here. So under excited state, what will happen? The electron, okay, from here, they will come over here. Because why? Each of the carbon wants to be bonded to 3 other atoms. Okay, so you need to make sure that you have enough, okay, orbitals for them to take part in the reaction. So what happens? You are going to have this orbital S and then P2. That's why we have sp2 hybridization. Yeah. And what happens to the other electron? This is the other electron that will be donated into the ring. Yeah. So if you look at it, from which type of atomic orbital do the electron in part A come from? Okay, they do come from 2p orbital. Yeah. If you want to go in exact, then each of these orbital, they are given X, Y, and Z over there. So if you want, you can put 2pz. Yeah, also can. Okay. So what do we mean by the term delocalized electron in benzene? Yeah, delocalized electron, okay, they move around. Okay, they move around. So they are no longer associated to any of the carbon atoms. Okay, do remember they move around. Okay, free to move around. Okay, but if they ask you what is the difference, okay, between the pi bond between benzene and a normal, alkene. Okay, the difference, okay, is going to be the alkene, okay, the pi bond is actually the pi bond is going to be the electrons are still, okay, above, okay, the 2 carbon atoms that they are bonded. Yeah, like for example, hex 3 in, okay, if you have hex 3 in, okay, this one position 1, 2, and 3. So this is going to be double bond. It means that, okay, this is the pi bond. So it is on top of this carbon and this carbon only. Yeah, they move around that. Okay, not the other 2 carbons on the left, on the right. Yeah, so they are not going to move there. So that is going to be the difference. Yeah, they are no longer, okay, associated with any particular carbon atoms in the molecule. And this is the one that will make the benzene structure very, very stable. Yeah, and as I told you, for the third time, I'm going to use the term. Okay, the term is going to be, okay, remember just now I say aromatic stabilization. Yeah, aromatic stabilization. Okay, let's actually move on. Okay, so now you know, yeah, about benzene. Yeah, now you know about the name. Yeah, now you know a little bit about benzene. Yeah, so the next part is going to be know about the reactions of arenes. Yeah, the reactions of arenes. So you can see, yeah, the delocalized pi bonding electron, they remain intact for most of the reaction. Okay, for most of the reaction, they remain intact. Okay, because, okay, as I told you, aromatic stabilization. Yeah, aromatic stabilization. Okay, but, okay, if there is a reaction, okay, like for example, okay, if you have like, okay, we know that there is a circle over there, okay, which is going to be the pi bonding or the pi ring, yeah, benzene ring. So you know that, okay, in the benzene ring, there are 6 electrons. Okay, if you have 6 electrons, what are attracted towards electrons? So everyone should know electrophile. Okay, electrophile is electron loving. Yeah, so electrophile will be going towards the benzene. Yeah, so that's why they say, yeah, the high density around the benzene ring will attract electrophile. Yeah, will attract electrophile. So, okay, we have learned a lot of different types of mechanism. Yeah, so if I put it over there, free radical substitution. Yeah, we learn for carbon-carbon single bond. Yeah, for alkane, and we learn for carbon-carbon double bond. Okay, we actually learn they have electrophilic addition. And later on, we learn for alcohol and halogenoalkane, yeah, it's going to be nucleophilic substitution. Okay, and then for carbonyl compounds, yeah, aldehyde and ketone, we learn about, okay, the nucleophilic addition. The only thing that is we didn't explore yet is going to be electrophilic substitution, which is going to be what we are going to learn today. Okay, which is going to be electrophilic substitution, okay, will be applied, okay, when it comes to arene molecules. Yeah, so the first one, okay, you can see from the syllabus at the top, okay, they want you to know about the substitution of Cl2 and Br2. Yeah, the difference, okay, I put it over here, the catalyst that I put in my notes, okay, I put it FeBr3. Yeah, I don't want you to get confused. Okay, FeBr3 was actually put in the textbook, okay, the textbook that you have now. Okay, but because there is a change in syllabus, okay, please have a look at this part over here. They have removed the FeCl3 and FeBr3. They have replaced it with AlCl3 and AlBr3. So this one is something that you want to take note. Yeah, but I still put over that. Yeah, so it do happen with FeBr3. Okay, but in your syllabus, okay, they are requiring you to remember AlCl3 or AlBr3. Yeah, so in this case, it will react with Br2. Yeah, with a catalyst. Okay, if I want to follow the syllabus, I supposed to follow AlBr3. Yeah, so this one, okay, I just show you over here so that you don't get confused, okay, with your textbook and, okay, with the current syllabus. But we need to follow the current syllabus also. Yeah, so you can see over here what happens. Okay, basically, yeah, we know that, okay, the carbon is attached to hydrogen over here. Okay, all the carbon, okay, each of them is attached to one hydrogen. What happens is, okay, you are going to replace this hydrogen, okay, with Br. Yeah, you can see replacing the hydrogen with Br. When you replace, yeah, that is going to be substitution. You are not adding, you are replacing. So if you are replacing and you remove the H, okay, the H will join with another Br, you will get HBr. So therefore, this is going to be the equation, yeah, the equation for this. Anhydrous means without the presence of water, right? Now, if you put over there, okay, so you can actually change accordingly. Yeah, if you have this catalyst, okay, you can remove this part, okay, and you say react with catalyst. The electrophile from the catalyst, so I remove this part, AlBr3 polarizes a bromine molecule. Okay, and then the bromine molecule, okay, is going to actually give you the it will actually form a dative bond, okay, and then they are going to give you the electrophile of this. Yeah, so and we will have the, okay, we will have the mechanism of the reaction. Okay, of course, okay, if you look at it like this, of course you will not understand. Yeah, but I will show you again. Yeah, I will show you again. Okay, with, okay, with in a while. Yeah, I'll show you the mechanism again in a while. Okay, but basically what happens, okay, the catalyst will give you, okay, the catalyst will give you the electrophile. Okay, and the electrophile, what happens, the electrophile is going to be attracted towards the benzene. So that when you draw the curly arrow diagram, you must show the movement of electrons. Okay, so they will form, okay, a new bond with the Br. Yeah, so when you form bonds, you require 2 electrons. It means that 2 electrons, that earlier we have 6 electrons. Okay, so 2 electrons from the 6 electrons in the ring, okay, they go and form the bond with Br. Yeah, so now you only have 4 electrons, okay, or it is going to create, because the electron went out, okay, it's going to create a positive charge over there. And this positive charge is going to be distributed equally with 1, Okay, if I put it over here, 1, 2, 3, 4, 5, 5 carbon. Yeah, the positive charge is going to be distributed with the 5 carbon. And now, because earlier I told you aromatic stabilization, okay, they want to be stable. Yeah, they said, why you go BR go and take my 2 electrons? I want the 2 electrons back. Yeah, how do they get the 2 electrons back? Yeah, you go away with BR, never mind. I'm going to take the 2 electrons from the hydrogen earlier. Okay, so the electrons will start to come in over here. So you are going to have, okay, heterolytic fission. Okay, you are going to have heterolytic fission, and you are going to have the H. Yeah, H is coming out to become H plus. Okay, so you will have this. Okay, and this H plus, what this H plus will do? Yeah, the H plus will join, yeah, with the catalyst, the product of the catalyst, and they will give you all this. Okay, but I need to rewrite this again. Okay, because it's involving FeBr3. Okay, but if I put this, okay, if I move on, okay, they say just now I wrote about bromine. Yeah, they can also have, okay, reaction with chlorine, similar. Okay, similar, but you replace this with AlCl3. Yeah, so no need this one, change it. Okay, they are going to actually react with AlCl3. Therefore, okay, therefore, AlCl3 and AlBr3, apart from calling them as catalysts, okay, we do call them as halogen carriers. Yeah, later I'll show you also why they are called halogen carriers. Yeah, so let's say now I want to write the mechanism similar to the one on top. Okay, for the reaction of benzene and chlorine gas. This is the part that you listen carefully. I will go through one by one. Yeah. So here, okay, you are going to have a reaction with benzene and chlorine gas, and I want to actually write the reaction. So the first thing that you need to do is, okay, you need to decide what is going to be your catalyst or your halogen carrier. If you have Cl, automatically it's going to be AlCl3. Done. Yeah, AlCl3. So what you need to do is going to be, you put the AlCl3, you bring it closer to Cl2. So Cl and Cl, I put over here. Yeah, Cl2. What happens, okay, when the AlCl3 go near to the Cl2, polarization will happen. So the electrons, okay, will move, okay, from one side of the Cl to become delta negative, and this is going to become delta positive. So what happens next is going to be, okay, the one that is going to be more negative, okay, the one, because remember the curly arrow is to show the movement of electrons. So the arrow will be moving from Cl minus to here, and they will give you, yeah, AlCl4 minus, okay, they will give you AlCl4 minus plus Cl plus, yeah, and this is already going to be the electrophile that we want. Yeah, so the next step is going to be, now you just need to bring the electrophile over here. Okay, you put the electrophile over here. Okay, when you have say electrophile, go and attack benzene, go and attack like this. Don't do this. Yeah, don't do this. Okay, thing is not shown. Yeah, currently. Hold on for a while. Yeah, let me share the screen again. Okay, just yes, I'm lighting. Yeah, I'm sharing the screen again. Yes, hold on. Okay, they actually what they do, they go and, okay, put the arrow like electrophile will go and attack the benzene. Yeah, they put it like that. Okay, but this is wrong. Yeah. electron, okay, in the benzene ring. Yeah, so you need to remove that and you put the electron movement like this. Yeah, so that is going to be the one that is going to be happening. Okay, so if you have this, okay, just to check, okay, can you guys hear me, Mr. Joseph? Can you hear me?
Yes, sir.
Okay.
Yes.
Okay, I'll continue. Yeah. So if you have this, okay, what happened? Yeah, I told you from having 6 electrons, the 2 electrons, because earlier they had hydrogen over there. So the 2 electrons, okay, is going to be shared. Okay, you are going to have something like this, incomplete. Want the electrons back. Okay, they want the electrons back. So in order to get that electron, okay, you just need to bring the electron back into there. Okay, so you need to bring it back. Okay, that is going to be going to complete, yeah, going to complete the benzene ring. So you will have something like this. Okay, going to complete the benzene ring. And you will have Cl, but what happens to the H? H will become H plus. Yeah, H will become H plus. And what will happen to the H plus? Remember, okay, there is going to be AlCl3 is known as halogen carrier. They are carrying the halogen over here. Okay, so what happens? The AlCl4 minus now, okay, H plus will join with the AlCl4 minus, and they will give you AlCl3 again with HCl. You are going to get the catalyst again, okay, with HCl. So that is going to be, normally when we write, okay, we say AlCl3, HCl. Yeah, they will put it over here. So this is going to be the mechanism of the reaction that will happen. Yeah. So that is going to be to explain about the mechanism of the reaction. If it is going to be with Br2, yeah, very simple. Change all the Cl over here that you can see to Br. That's it. Yeah. So the catalyst also will become AlBr3. Yeah. So you need to know, important thing over here is you need to know how to draw the curly arrow. Yeah. To show the movement of the curly arrow as the movement of electrons. Yeah. That is going to be very important. Yeah. So I will move on. Yeah. So earlier, okay, we actually look at benzene. Yeah, earlier we look at benzene, and I told you arenes. Yeah, benzene and methyl benzene. We are going to learn about methyl benzene also. Yeah, so you can see here, this is going to be methyl benzene. Okay. And when methyl benzene and other alkyl arenes, yeah, what is other alkyl arenes? Yeah, instead of methyl, maybe they put ethyl. Yeah, so this is going to be alkyl arenes also. I'll just draw it here. Okay, if you have a benzene and they put C2H5, this is also alkyl arenes. Yeah, so whenever you have alkyl arenes, they say that, okay, the same reaction, okay, you will have electrophilic substitution reaction. But the position of the substitution is going to be at position 2 and 4. Okay, this is going to be, last time we have studied about this. Yeah, we have studied about electron withdrawing group and electron donating group. Yeah, so when it comes to electron donating, yeah, alkyl groups, yeah, they are electron donating. So the CH4, okay, they are going to donate the electron. And if they are donating the electron, they are going to activate position 2 and 4. What is position 2 and 4? This is position number 1. This is position number 2, position number 3, position number 4, 5, and 6. Okay, position number 2 and 4, which is actually the same as 2, 4, 6 actually. Yeah, later I'll tell you. Yeah, it's supposed to be position 2, 4, 6. Okay, so if you have this reaction, you can see they are going to have, yeah, they will still use the AlCl3. Okay, they will still use the AlCl3, which is going to be the catalyst or the halogen carrier. Okay, so it is very important. Okay, if you want to substitute into the benzene ring, you must have, okay, halogen carrier. Without halogen carrier, you cannot substitute into the benzene ring. Very important. Yeah. But if you have methyl benzene, you will have a mixture. Yeah, you are going to have position number 2 activated. Cl can go there, and Cl can go at position number 4. Okay, and Cl can also go to position number 6. Okay, but do remember, if they go to position number 6, this and this, they are the same. Yeah, the same structure. Okay, so therefore they say 2 4. Yeah, so you will get a mixture of the compound. Yeah, but the others are going to be the same. Yeah, so they say that it is going to be activated because electron donating group. Yeah, so you need to remember other electron donating group. We will discuss this in a while also. Okay, they are going to be other electron donating group. You need to remember phenol, yeah, OH, yeah, and phenylamine, NH2, they are also electron donating. Yeah, so we get a mixture of compounds. Okay, but if you have excess chlorine, yeah, what will happen if you have excess chlorine? Then you are going to have a mixture of compound. You see so many. Okay, so if I put it as so many over here, because just now, okay, they only replace one by one. Okay, so if you have, like for example, in excess, I'll draw for you. Okay, if you have, okay, a methyl benzene, and then the Cl2 is in excess, okay, what happened? Instead of substituting it one by one at position 2 4 6, they are going to actually substitute double first. Okay, like for example, like this, CH3, they will substitute at position number 2 and 4. They can substitute at position, okay, if I draw, position number 2 and 6, or they can actually substitute at this all the position 2 4 6 position. Okay, so Cl, Cl, Cl. Okay, so this can happen. Yeah, this can happen, and of course, okay, you are going to have HCl. How many HCl? You can count 1 2 3 4 5 6 7 7 HCl. Okay, so this one is going to be 7. Okay, this one, if you want to balance, is 3. Yeah, so anyway, the balancing is not important. Yeah, so in this case, we want to know that this thing can happen, and in order for this to happen, you must have AlCl3 anhydrous. Yeah, halogen carriers must be there. Yeah, so this happens in excess. If it is not in excess, then these two only. Yeah, so next, okay, is going to be, okay, the next part is the bond strength, okay, between carbon halogen in halogenoarenes. Yeah, so if you put, like for example, if I have carbon and I have Br under normal condition, halogenoalkane, and if I compare, okay, the bond, okay, between benzene and carbon and Br over here, it is found that, okay, the bond, okay, this particular bond between carbon and Br is more stronger. Okay, and if they ask you what is the reason, yeah, why this one is more stronger compared to this particular bond, yeah, why this is stronger, okay, the reason is, okay, similar, okay, the Br, okay, they will have a lone pair of electrons. So this lone pair of electron, okay, they are going to be entering, or some kind of a slightly overlapping, yeah, overlapping with the pi bond, or slightly overlapping with the benzene ring. Yeah, so when they are overlapping orbitals, and orbitals, when they overlap, yeah, they will give you some sort of a double bond character. Yeah, when they have double bond character, yeah, it's going to be difficult to be broken. Sometimes students don't understand why double bond difficult to be broken. Yeah, if you are in taekwondo or something, you have a piece of plywood, okay, you arrange them, and then there is one piece of plywood, and you have two pieces of plywood this length, yeah, and they ask you to go and break the piece of plywood. Okay, in this case, if you break, most probably the plywood will break, but if you try to break this, most probably your hand might be breaking. So in this case, yeah, we know that if you have more bond, yeah, or if the bond length becomes shorter, okay, it's going to be more difficult to be broken. The bond energy is going to be more. Therefore, you need more energy to break this bond. Yeah, so coming back here, they say the carbon halogen bonds are stronger. Why? Because one of the lone pair of the halogen, they overlap slightly with the pi bonding system. Yeah, and that will give you a partial double bond character. Okay, don't focus on the reaction. Yeah, they will give you the partial double bond character that will make them stronger compared to normal halogenoalkane. Difficult to be broken. Yeah, difficult to be broken. So this is going to be additional part over there. Now, we do have, apart from electrophilic substitution, we do have other reactions, which is going to be free radical substitution. Okay, and you have learned about free radical substitution. Okay, free radical substitution happens in alkanes. Okay, under the presence of UV light. Okay, if I react with Br2, okay, slow reaction with the presence of UV light, or sunlight. Okay, the reaction is going to happen where you are going to have one by one of the hydrogen will be replaced. Okay, and the bromine water will become decolorized and so on. Yeah, we know that. Okay, but when it comes to benzene, benzene do not undergo free radical substitution. Okay, why? Okay, because benzene do not have the methyl group. Yeah, this one is going to be the alkyl groups. It means methyl benzene, ethyl benzene, they can actually undergo free radical substitution. Okay, with the presence of UV light. So not only with chlorine gas, Br2 gas also can. Yeah. No substitution in benzene ring. Remember just now, if you react with Br2 or Cl2, the Cl or Br will not come over there. Yeah, why they won't come over there? Because in order to go there, you need to have halogen carriers or the catalyst. Yeah, so in this case, we are not using the catalyst. Yeah, so it's going to be the substitution of free radical substitution is going to be focusing on the side chain, which is going to be the CH3. So if you have CH3, one of the H is going to be replaced by Cl. And maybe the reaction will continue, replace one by one, Cl. Okay, then continue, replace another one, maybe Cl. This one is all you have learned last time. Yeah, but the only thing that is going to be different over here, which I highlighted over here, okay, I bolded over here, boiling. You must boil them. Yeah, so it requires, okay, remember benzene, they kind of stable. Yeah, so in order to actually get them to react, it's going to be a little bit difficult. Yeah, so boiling, okay, it must be boiled. Yeah, so the next checkpoint over here, okay, I think this checkpoint you can actually do it yourself. Yeah, so basically I went through all the mechanism and so on. Yeah, you can go through yourself, no problem. Yeah, all the answers are there. Okay, but the next part, okay, that I want to go through with you is going to be known as nitration. Yeah, nitration of benzene. So what is nitration of benzene? Basically, you are adding the NO2 group. Yeah, if you have a benzene, okay, you are adding the NO2 group over here. Yeah, that is nitration. Yeah, so the electrophile, okay, the electrophile is going to be NO2 plus ion. Yeah, they are known as nitronium ion or nitrile cation. No need to memorize the name. NO2 plus is already good already. Okay, how do you make NO2 plus ion? Similar like just now. Yeah, when you have the catalyst with Cl2, they will react and give you the electrophile. Similar to that, you need to use concentrated nitric acid and H2SO4, and you will follow this particular reaction. Yeah, what is important is you are going to get the electrophile. Yeah, whether you want to make sure. Okay, okay, I think I got disconnected for a while. Yeah, but I'll just you need to know, okay, the equation. Okay, the equation. Okay, it's very important to know the equation. Okay, and we call it as this mixture, okay, of concentrated sulfuric acid and concentrated nitric acid, okay, as a nitrating mixture. Okay, we call it as nitrating mixture. Okay, let me share the screen again. I think the screen sharing stopped. So you need to have the nitrating mixture, okay, because I want to get the electrophile, yeah, and so the reflux in with benzene at 55 degrees Celsius is found in the textbook. Okay, but in your syllabus, okay, they mention 25 to 60 degrees Celsius. Yeah. So this one I'll put it also over there. Yeah. So you need to know. Okay, but basically I'll show you. Yeah, to save time, I'll show you how to write the mechanism. Yeah. First thing, yeah, you are going to have a benzene. Yeah, and you are going to have the nitrating mixture H2SO4 concentrated and HNO3. Yeah, so what is going to happen, they are going to react. Yeah, so this one, if you memorize, is good lah. Yeah, you can write very fast. Yeah, so they are going to give you NO2 plus and then 2HSO4 minus. Okay, and they will give you H3O plus. Yeah, this one I'll leave it to you how whether you want to memorize or not. Yeah, but if you keep on practicing, yeah, of course you can actually get it easily. Yeah, so this is the electrophile. Yeah, electron doubling. Yeah, so the electrophile. Okay, they will come over here. Okay, so similar like what we have done earlier. Okay, the electron. Yeah. Electron rich area is going to be the circle. Yeah, so it's going to be from the benzene ring will go to NO2. So what happened next is going to be the benzene ring is going to be broken. You will have like this. Okay, used to have H, but now new bond is going to be formed. Yeah, and what happens now, because they want the electrons to come back. Okay, the two electrons over here, they will come over here. Okay, they will form, okay, the nitrobenzene. Okay, you will get the nitrobenzene and then left with H plus. Okay, left with H plus. Okay, remember what happened. The H plus can either react with this and so on. Yeah, to give you the H2SO4 and so on. But this is going to be the mechanism of the reaction. So basically, if you're wondering what is here, yeah, it's all there. Yeah, it's all here. And the same thing, if you look at all these slides, yeah, basically the same thing, okay, that we have discussed earlier is all there. Yeah, so basically you can read. Yeah, I have already go through that. Okay, but the only thing, yeah, that is going to be additional over here is, okay, do remember this is NO2 nitro. Okay, nitro is going to be electron withdrawing group. Yeah, they are electron withdrawing group. Yeah, therefore, okay, they are going to be slightly different than the methyl benzene. They are going to be known as 1, 3, 5 directing or 3 and 5 directing. Yeah, so the position, yeah, the activated position of the benzene is going to be different for nitro. So therefore, if you have further nitration, okay, if you have already one NO2 there, and the NO2 can continue to jump in, yeah, it can still go further, okay, but okay, what are the positions that will be activated? The position will be 1, 3, yeah, this is 3, and then maybe after that you will have 5, which is this. Okay, so they are going to activate all these 1, 3, 5 position. And to answer the question why different than methyl benzene, okay, because methyl benzene, methyl group is electron donating, is 2, 4, 6 directing, but now NO2 is electron withdrawing. They will activate position 3 and 5. Okay, so if you look at this table, yeah, this table, okay, is just tells you, yeah, about which one is electron withdrawing, which one is going to be electron donating. And if you look over here, yeah, I have also included the one from your syllabus. Okay, they say that you need to know the effect of the following. Yeah, but the one that we studied over here, this one, I think there's a mistake, CH3. Yeah, so methyl or alkyl group, they are electron donating. Yeah, and there are others that they want. Yeah, so this one is going to be, we already studied. Okay, amine group and phenol, the OH hydroxyl group. Yeah, they are also going to be electron donating group. Okay, so that's going to be additional stuff over there. And yeah, when it comes to electron withdrawing, okay, we know this one. NO2, nitro, is going to be electron withdrawing. Yeah. So, but in your syllabus, okay, apart from NO2, they want you to also focus on carboxylic acid group and COR. Okay, this one is going to be the ketone whenever they have the ketone over there. So there are certain things that you might want to focus. Yeah, you might want to focus whether they are going to be electron donating or electron withdrawing or what activating and so on. So this is 2, 4, 6. This is going to be 1, 3, 5. Yeah. So the rest, yeah, I think I wanted to start about this, but I think it's better to hold on first. Yeah, for alkylation, yeah, we have alkylation, yeah, we call it as Friedel-Crafts reaction, but it actually can be done very fast. Yeah, but we no need to rush. Yeah, no need to rush. Yeah, but if you look at the summary, yeah, what we have covered for today. Yeah, in what we have covered today is basically we have learned about this. Yeah, they are going to actually react with Cl2 and Br2 with the presence of catalyst. I just want you to double check in your textbook, because the textbook used FeBr3, FeCl3, but they did mention AlCl3 also. Yeah, but now it is going to be changed, so try to avoid using this anymore. Yeah, try to avoid using this. Okay, but it's okay, you can still use it. Yeah, you can still use it. Okay, but the method, the mechanism and so on is still the same. Yeah, and the nitration, yeah, the nitration is going to be the temperature. Yeah, the temperature in your textbook. Okay, in the past we always use the 55 degrees Celsius. Okay, but now you can see they do accept 25 degrees Celsius to 60 degrees Celsius. Okay, we didn't cover this. Okay, we didn't cover this. Okay, this one we will do it next week, Monday. Yeah, and the mechanism. Okay, so the mechanism we have done, nitrobenzene. Aromatic stabilization, yeah, is very important. Okay, you just need to put aromatic stabilization to explain why, okay, substitution is preferred, okay, instead of addition. Yeah, why you have substitution reaction. Yeah, and okay, you we need to find out, yeah, when the halogen they go to the side chain, when they actually go to the ring. Yeah, so this one, to the ring, they must have the halogen carrier. Yeah, they must have the halogen carrier. If not, they cannot go to the ring. Like, cannot go directly substituting the hydrogen bonded to the carbon. Yeah, over there. And then describe, okay, that in electrophilic substitution, yeah, you have different substituents. Okay, will give you different positions. Yeah, so we have already discussed about this as well. Okay, so we will actually next lesson, okay, we are going to actually look into detail, okay, about the other reactions. But do remember, yeah, there is going to be something in your textbook they didn't cover. Yeah, this is newly added. Yeah, newly added hydrogenation of benzene ring using H2, okay, and platinum and nickel catalyst. So this one, do remember, hydrogenation, this is going to be no longer no longer electrophilic substitution. This is addition. Okay, and I told you, okay, because of the aromatic stabilization, addition normally don't happen. Okay, but addition can happen if under harsh condition. Yeah, so that's why you need to have heat. Yeah, they didn't put over here. Normally they say high pressure also. Okay, it's slightly similar with your carbon-carbon double bond with the hydrogenation of alkene. Yeah, the hydrogenation of alkene, you use platinum and nickel with 140 degrees Celsius. Yeah, so that one, yeah, is going to be similar, but I think this one is going to be more harsher condition. I think you need more temperature higher than 140, but they didn't specify. Yeah, they didn't specify. Therefore, I want you to focus over here. Don't miss out. It is not in your textbook. Okay, so the rest, they are all in your textbook. Yeah, so later part, okay, next week Monday, we will actually go through the remaining part that we didn't do, and probably we'll enter phenol. Yeah, we'll learn about phenol. Okay, with that, yeah, I'm done for today. Okay, make sure, okay, you go and complete your reflection. Yeah, so so that you can write down what you have learned and so on. Yeah, so I'll put this video, okay, recording, yeah, so that you guys can see. Yeah, that's it from me today. Yeah, thank you guys. Okay, bye.
Thank you, Mr. Gopi.
Yeah,
Thank you, sir. Bye, sir.
bye. See you.
Bye, sir.
See you. See you. Bye.
Thank you, Mr. Gopi. Bye-bye.
Thank you, Miss. Bye.